Right now, outside your window, it might be raining. You might hear the gentle rustle of wine through the trees. But far away, in depths beyond your wildest imagination, the sky tells a very different story. Imagine worlds where the clouds don't drop water, but pure diamonds. Where the wind defies the speed of light, and storms of jagged glass tear through the darkness. This is where physics falls silent, and nature becomes a wild, cosmic artist. Tonight, we leave the familiar climate of Earth behind. We are embarking on a peaceful journey into the heart of the most impossible weather in the universe. Lean back, close your eyes, and let the impossible storms carry you into a deep, effortless sleep. Welcome to a world of beautiful, lethal illusions. Tonight, we leave behind the gentle rains and familiar winds of Earth. We journey to our closest planetary neighbor, a world that from afar gleams like a jewel in the twilight sky, a beacon of serene beauty. But as we draw near, the illusion shatters. This is not a sister world. This is a warning, a cosmic experiment in runaway climate change taken to its absolute, terrifying extreme. This is Venus, and this is the story of its reigns of hell. In our night sky, Venus is the morning star, the evening star, the brightest object after the moon. For millennia, poets and dreamers looked up and imagined lush tropics, steaming jungles, perhaps even civilizations beneath those perpetual, reflective clouds. The truth, uncovered by robotic probes braving its inferno, is a reality so harsh it recalibrates our understanding of what a planet can become. Venus is a planet of superlatives, all of them deadly. It is the hottest planet in our solar system, with a surface temperature averaging 864 degrees Fahrenheit, hot enough to melt lead, zinc, and even some types of steel. Its atmospheric pressure is 92 times that of Earth's at sea level, equivalent to the crushing weight found nearly a kilometer beneath our ocean surface. And those beautiful, bright clouds that reflect 75% of the sun's light, they are not made of water vapor. They are a perpetual, global haze of sulfuric acid. Our story begins not in the hellscape of today, but in a distant, almost mythical past. Scientists believe that Venus, in its infancy, may have been surprisingly Earth-like. It formed at a similar distance from the Sun, was of similar size and composition. It likely had vast, shallow oceans of liquid water. For perhaps 2 billion years, Venus and Earth were siblings, two blue marbles adrift in the early solar system. But somewhere a divergence began. A tipping point was reached. On Venus, volcanic activity may have been cataclysmic, releasing unimaginable quantities of carbon dioxide into the atmosphere. Without a robust system of plate tectonics or liquid water oceans to sequester that carbon into rock, as happens on Earth, the CO2 built up, and built up, and built up. This triggered a runaway greenhouse effect. As temperatures rose, any oceans began to evaporate furiously, pumping vast amounts of water vapor, itself a potent greenhouse gas, into the atmosphere. The planet warmed further, baking the surface, releasing more CO2 from carbonate rocks. It was a positive feedback loop with no off switch. The climate spiraled out of control. The oceans boiled away entirely, their water molecules broken apart in the upper atmosphere by solar radiation, their hydrogen lost to space forever. Venus was left a desiccated, superheated rock, shrouded in a thick, suffocating blanket of CO2. And into this dry, CO2-rich atmosphere, sulfur entered the mix. Volcanic eruptions, which likely continued in epic, resurfacing events, pumped sulfur dioxide high into the sky. There, combined with the traces of water vapor and sunlight, to form droplets of sulfuric acid, H2SO4. Thus, the iconic clouds of Venus were born, a global, corrosive shroud floating about 50 to 70 kilometers above the scorching surface. This is where Venus's most eerie and paradoxical weather phenomenon occurs. It rains acid, but the rain never reaches the ground. Imagine a world where a perpetual, global drizzle of concentrated battery acid falls from a yellow-tinged sky. But the lower atmosphere of Venus is so incredibly dense and hot that as the sulfuric acid droplets fall from the cloud decks, they encounter rising temperatures. Long before they could ever strike the surface, they evaporate. The sulfur compounds rise back up on convective currents, only to condense into clouds once more. It is a perpetual, toxic hydrological cycle, a rain of hell that forever falls into its own evaporation. As you begin to visualize this, let the soundscape deepen. That low furnace hum is the sound of a massive, dense atmosphere in motion. The static-like crackles are the faint, distant echoes of chemical processes in the cloud tops, perhaps even the weak sizzle of acid droplet formation. There's no thunder here, no howling wind as we know it yet. The violence of Venus is slow, relentless, and thermodynamic. But there's wind. Oh, there's wind. At the surface, the air is so thick that it moves with the languid pace of syrup. A breeze here would not rustle a leaf. It would feel like wading through a heavy, hot liquid. Yet, this dense air is driven by colossal forces. The entire atmosphere of Venus is engaged in a phenomenon called superrotation. While the planet itself rotates painfully slowly, a Venusian day is longer than its year. The upper atmosphere screams around the planet at up to 360 kilometers per hour, completing a full circle of the globe in just 4 Earth days. It is as if the planet is standing still while its sky is whipped into a frenzy around it. We are floating now in this liminal space. Above us, the high-speed jet streams of the upper cloud decks. Below, the impossible heat and pressure of the surface, shrouded in a perpetual, dim, reddish glow. The sun is a diffuse, blurry patch of brightness you could stare at without blinking. The light that filters down has been scattered and absorbed by the deep atmosphere. The sky is a monotone, oppressive orange. This is a world without seasons, without day-night temperature swings, without respite. It is a world in a state of permanent, violent equilibrium, a pressure cooker planet. But before we descend into the deepest hell, let us pause here in the acid clouds. There's a strange, terrifying beauty in this machine-like efficiency. Venus is a lesson in extremes, a demonstration of the awesome power of planetary physics when left unchecked. It shows us that a world can be stunningly beautiful from a distance and utterly unforgiving up close. It is nature's most elegant and deadly trap. As you listen, imagine yourself a solitary, indestructible probe, drifting in those yellow clouds. Around you, droplets of acid form and evaporate in a silent, endless dance. The heat is immense, but here, it is not yet lethal. There's a strange, muffled peace in this eternal chemical factory in the sky. The violence is slow, chemical, absolute. We're about to go deeper. The descent awaits. Tio, understand the true nature of Venus's weather. We must venture below the clouds, into a realm no human eye has ever seen directly, a place visited only by a handful of hardened Soviet landers in the 1970s and 80s. Their transmissions, lasting mere minutes before succumbing to the heat and pressure, painted a picture of a truly alien hellscape. Our descent begins. As we leave the sulfuric acid cloud decks, the light fades rapidly. The thick, carbon dioxide atmosphere acts like a series of increasingly dense filters. The bright, diffuse orange dims to a deep, murky red, then to a perpetual, twilight gloom. The temperature, already high in the clouds, begins to climb exponentially. The pressure mounts, a physical weight on your imaginary spacecraft, on the very atoms of the air itself. This is not an atmosphere as we know it. At the surface, the pressure is 92 times that of Earth's at sea level. To stand on Venus would feel like being submerged under 900 meters of water. Every movement would be a colossal effort against the viscous, supercritical air. The carbon dioxide here is no longer a gas in the familiar sense. It behaves more like a superdense, hot fluid. And then there's the wind. At the surface, the howling superrotation of the upper atmosphere has been slowed to a crawl by friction and immense density. But do not mistake this for stillness. The winds here are slow, powerful, and relentless. They move at walking pace, perhaps 5 to 10 kilometers per hour. But because the air is so dense, these gentle breezes carry immense force. They would not blow you over. They would push you with the steady, unstoppable pressure of a deep ocean current. They are winds that sculpt not sand, but rock, over geological timescales. This leads us to one of Venus's great mysteries. Its surface is surprisingly young and smooth. There are few impact craters, suggesting a global resurfacing event, or events, within the last billion years. The leading theory is one of epic, planet-wide volcanism. Venus may not have plate tectonics like Earth, but it seems to release its internal heat in catastrophic outbursts. Imagine not a single volcano, but thousands, perhaps millions, erupting simultaneously across the globe, flooding the plains with vast seas of lava that then slowly cool into the barren, basaltic landscapes we see. In this context, the weather of Venus extends to its geology. The thick atmosphere and high temperatures mean that the surface rock itself is pliable, like warm plastic. Mountain ranges may slowly sag under their own weight. The high atmospheric pressure suppresses the formation of steep, sharp features. Even the rocks themselves weather in alien ways. Without water, there is no erosion as we know it. Instead, the surface minerals likely interact chemically with the hot, acidic atmosphere, slowly altering their composition in a silent, thermochemical dance. Now let us land. Picture the Venera landers, squat, titanium spheres bristling with instruments, their lenses protected by quartz windows that would soon cloud over. They touch down on a rocky plain, lit by the dim, diffuse glow of a sun that is just a bright patch in the perpetual overcast. The sky is a dull reddish-brown. The horizon is lost in haze just a few kilometers away. The ground is not sand, but a cracked, slab-like pavement of volcanic rock, perhaps still warm from geologically recent flows. The sound here is not of wind whistling, but of wind pushing, a deep bass rumble, the sound of 1 trillion tons of atmosphere in slow, global circulation. It is the sound of a world breathing, a single, deep, scorching breath held for eons. There is no other life, no rustle, no call. Only the eternal, pressing hum of the furnace and the faint, gritty whisper of superheated dust against the lander's hull. And yet, within this hell, there's a perverse form of stability. Venus is not a planet of violent storms in the terrestrial sense. It is a planet that is a storm, a single, system-wide, thermodynamic storm. The entire world is an engine, with the sun's energy driving the superrotation of the upper atmosphere, and the planet's own internal heat driving the slow, convective churn of the lower atmosphere. The acid rain cycle is just one cog in this vast, slow-moving machine. This stability is what makes Venus so haunting. Earth's weather is chaotic, youthful, and full of temporary violence. Hurricanes that form and dissipate, fronts that clash and pass. Venus's weather is ancient, settled, and total. It is the climate of a finished world, a world that has reached its end state. It is a vision of what happens when the greenhouse effect wins, completely and irrevocably. As you sit with this image, a world under a perpetual, pressurized, hot dome, consider the message it carries for us on Earth. Venus is not merely a foreign planet. It is a mirror, held up to show us one possible, extreme end of the path we are walking. It demonstrates the awesome power of an atmosphere to shape, and ultimately to doom, a world. But our journey on Venus is not quite complete. There's one more layer to this atmospheric onion, one more twist in its meteorology that takes us from the deep hell of the surface back up into the clouds, to a phenomenon that is both beautiful and bizarre, the possibility of lightning. As we ascend from the oppressive silence of the surface back into the churning, acid-laced clouds, we encounter the final, enigmatic element of Venusian weather, its electrical personality. For decades, scientists have debated, does lightning strike on Venus? On Earth, lightning is born from a collision of ice particles and water droplets and towering thunderclouds, separating electrical charge. Venus has no water ice in its clouds. It has sulfuric acid and complex sulfur allotropes. Yet multiple spacecraft, from the Soviet Venera probes to the European Space Agency's Venus Express orbiter, have detected strong electromagnetic signals characteristic of lightning. Not the brilliant forked bolts that split our sky, but something perhaps more pervasive, vast, sheet-like discharges within and between the cloud layers, a continuous, planet-wide flickering in the toxic haze. Imagine this, in the perpetual, yellow twilight of the cloud decks, the very droplets of sulfuric acid, churning and colliding in the violent super-rotating winds, may be generating static electricity. The chemistry here is alien. Sulfur, chlorine, carbon, and traces of water vapor interacting under intense ultraviolet light. This could create charge separations we barely understand. The lightning of Venus would not illuminate a landscape, for there is nothing to see. It would be a hidden fire, a crackle of energy in the belly of the chemical factory, briefly heating pockets of atmosphere to thousands of degrees, perhaps even forging exotic, transient molecules in its flash. This hidden electrical storm is a fitting metaphor for Venus itself, a world of intense, internalized violence, masked by a deceptively serene exterior. Its fury is not in howling gales, but in the silent, crushing pressure, the corrosive drip of acid, and the occasional, deep-seated electrical groan that reverberates through its thick skin. Our journey across this world of impossible weather now turns from observation to reflection. What does Venus teach us, beyond the facts of its pressure and heat? It teaches us about the fragility of balance. Venus and Earth are often called twins, born of the same stellar nursery, made of the same stuff. But somewhere in their youth, their paths diverged catastrophically. A slightly stronger greenhouse effect, a little less water to sequester carbon, a different volcanic history, and the delicate equilibrium that allows for liquid water, moderate temperatures, and a dynamic, life-friendly climate can shatter. Venus is the ultimate example of a climate tipping point that kept tipping until it reached a new, infernal stability. It is a world that failed the test of moderation. It also redefines what weather can be. We think of weather as rain, snow, wind, and sunshine, the behavior of water and air on a rocky surface. On Venus, weather is the behavior of supercritical carbon dioxide and sulfuric acid aerosol across a global, searing hot system. It is geology and chemistry and fluid dynamics blended into a single, planet-encompassing process. The rain never reaches the ground. The wind at the surface is a slow, viscous flow. The seasons do not exist. It is a planet-sized lesson in thinking beyond our terrestrial paradigms. As we prepare to leave Venus behind, let your mind's eye take one last look. See it not as a hell, but as a monument to the awesome, indifferent power of physics and chemistry. A world that is, in its own way, perfectly adapted to its own extreme conditions. Its atmosphere is not a mistake. It is the inevitable outcome of its history, the final, stable state of its complex system. Now, let the sounds of this world slowly transform in your mind. The deep electrical crackles begin to space out, becoming echoes of echoes. The oppressive furnace hum softens, losing its edge of overwhelming heat, becoming more like the resonant drone of a vast, empty chamber. The feeling of immense pressure lifts, replaced by a sense of spaciousness, of release. We are moving away. The orange gloom fades to a point of bright, reflected light in the black sky. The beautiful, deceitful evening star once more. The acid clouds, the silent lava plains, the slow, super-rotating winds, all recede into the cosmic distance. Venus remains a world of eternal, settled fury, a sentinel warning of climatic extremes. But our journey through impossible storms has only just begun. Venus is the closest, most familiar face of planetary weather gone wrong. As we venture further out into our solar system and beyond, we will encounter storms made not of acid, but of diamond. Winds that don't whisper or howl, but scream at supersonic speeds for millennia. Rains not of water, but of molten glass and liquid gemstones. Venus taught us about the end of a terrestrial dream. The next worlds will teach us about the sheer, boundless imagination of the cosmos. For now, let the last impressions of Venus dissolve. Let the final, deep pop of its distant lightning be the period at the end of its chapter. We leave behind the acidic, suffocating embrace of Venus and set our course for the outer solar system, toward the kings, the giants, the majestic behemoths that rule our celestial neighborhood. Tonight, we dive not onto a surface, but into an abyss. We journey to where the very concept of weather transcends wind and cloud and becomes alchemy. We go to the realm where carbon, the fundamental element of life, is subjected to such unimaginable forces that it surrenders its ordinary nature and becomes a gemstone. This is the story of Jupiter and Saturn. This is the story of diamond rain. From our distant vantage point on Earth, Jupiter and Saturn are jewels in the night sky. Jupiter a bright, steady beacon, Saturn, with its breathtaking rings, the crown prince of the cosmos. They are gas giants, worlds without a solid surface as we know it, but that term sells them short. They are not merely balls of gas. They are vast, dynamic, layered spheres of mostly hydrogen and helium, with hearts of mystery and atmospheres of epic violence and sublime beauty. Our story begins not at the colorful cloud tops, those famous bands of tan, orange, and white, the great red spot, but far below them. To understand the diamond rain, we must first take a conceptual dive, a descent into pressure so extreme it defies earthly analogy. Imagine sinking into Jupiter's atmosphere. The first few hundred kilometers are a realm of familiar-ish weather, albeit on a gargantuan scale. Ammonia ice clouds give way to ammonium hydrosulfide, then to water ice clouds. Winds scream at speeds over 500 kilometers per hour, confined in jet streams that are stable for centuries. Storms larger than our entire planet brew, merge, and rage. But this is just the outer skin, the turbulent facade. As we sink deeper, the light from the sun fades to nothing. The temperature and pressure rise exponentially. The gaseous hydrogen atmosphere, under the immense weight of the layers above, begins to behave strangely. Around 1,000 kilometers down, the pressure reaches about 200,000 times Earth's atmospheric pressure. Here, hydrogen undergoes a phase transition. It becomes liquid metallic hydrogen. This is now liquid like water. It is a quantum fluid, a sea of protons and electrons that can flow like a liquid but conducts electricity like a metal. It is a state of matter that does not exist naturally anywhere on Earth. This ocean of liquid metal is thought to be the engine for the gas giant's powerful magnetic fields, fields that are thousands of times stronger than Earth's, trapping radiation in lethal belts and painting their poles with ethereal auroras. But we are searching for carbon. In the upper gaseous layers of these giants, carbon exists mostly as methane gas, CH4. As we descend into the deep, hot interior, the story of this carbon begins its magical transformation in the searing heat, thousands of degrees Celsius, and crushing pressures, millions of atmospheres. Of the mid-layer, the sturdy methane molecules are shattered. The bonds holding the carbon and hydrogen atoms together are broken by the sheer force. The hydrogen, being light, tends to rise. The carbon, now liberated and subjected to this planetary forge, has a different destiny. Here in the dark, hot, high-pressure mantle of the gas giant, individual carbon atoms are squeezed, and squeezed, with no escape, and under the influence of overwhelming force, they begin to bond to each other in a rigid tetrahedral lattice, the atomic structure of diamond. Tiny seeds of carbon crystallize out of the fluid mix, and then they fall. In this vast, dark interior, where the very air is a superheated, pressurized fluid, a gentle, eternal precipitation begins. Not of water, not of acid, but of solid diamond. Graphite flakes may form first, but under these conditions, they are quickly compressed into the harder, more stable form. These diamond hailstones grow as they fall through layers of dense fluid, accumulating more carbon. Some models suggest they could grow to sizes of centimeters, perhaps even larger, forming a glittering, dark shower sinking toward the planetary core. Imagine this scene. Absolute darkness, save for the faint, deep thermal glow of the heated fluids. a pressure so immense it would crush any spacecraft into a speck, a temperature that would vaporize tungsten, and through this hellish environment, a slow, graceful, majestic snowfall of diamonds drifts downward, a serene counterpoint to the unimaginable forces at play. This is not a metaphor. It is a robust scientific prediction, based on high-pressure physics experiments and sophisticated planetary models. On Saturn, with its slightly higher carbon-to-hydrogen ratio, this diamond rain may be even more abundant. For eons, these worlds have been creating and raining diamonds in their hidden hearts, an unseen meteorological wonder of pure cosmic alchemy. As you begin to picture this, let the soundscape guide you deeper. The grand planetary hum is now joined by a new texture, a slow, deep, percussive ping, 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 as if vast, crystalline structures are gently settling against one another in the deep currents. It is not a harsh sound, but a resonant, low-frequency chime, the sound of geological patience, of a process measured in millennia per falling gem. We are floating in this inner ocean, witnesses to a storm of breathtaking value and profound silence. A storm where the precipitation is literal fortune, but where there is no one to gather it, no eye to admire its sparkle. It is nature's most extravagant performance, staged in a theater with no audience. But what happens when the diamonds reach the bottom? Do they form a layer around the core? A crust of gemstones over a heart of rock and ice? Do they eventually dissolve back into the soup of carbon under even greater heat and pressure near the core? The journey of the diamond, like the giants themselves, holds its secrets close. Before we seek those answers, rest in the image of this silent, glittering downfall. It is a reminder that the universe's wonders are not always for us. They exist in their own right, expressions of physical law on a scale and in an environment we can scarcely dream of. The diamond rain is beautiful not because it is rare on Earth, but because it is a perfect, inevitable consequence of a giant world's nature. Our descent into the realm of the giants has only begun. The diamond rain is one layer of their mystery. As we go deeper still, we will approach the final destiny of this glittering precipitation and confront the ultimate unknowns at the heart of a gas giant. As we sink deeper into the abyss, the diamond rain around us evolves. The tiny, glittering seeds have had time to grow. Swept in slow, deep currents of metallic hydrogen and helium, they collide, merge, and accrete. What began as a fine dust of carbon crystals may now be a shower of pebbles, then stones, and perhaps, in the most speculative and wondrous of models, even boulders of diamond, tumbling through the eternal night. This is weather stripped to its most elemental. There's no sunlight here to drive it, no Coriolis force from rapid rotation to spin it into bands. This is precipitation driven by pure gravity and thermodynamics. The heavier carbon, compressed into its most dense form, sinks. The lighter hydrogen and helium buoy upwards. It is a planetary scale sorting mechanism, a slow, relentless distillation happening over billions of years. But our journey follows the diamonds downward. Their destination? The very heart of the giant, the core. For all their gaseous majesty, Jupiter and Saturn are believed to harbor central cores. These are not the molten iron hearts of terrestrial planets. The cores of gas giants are thought to be a bizarre, dense amalgamation, a mixture of rock, ice, water, methane, ammonia, and possibly a vast mantle of exotic, superionic ices. And into this realm, the diamond rain finally arrives. What happens next is one of planetary science's great puzzles. One possibility is that the diamonds sink onto this core, forming a glittering, diamond-rich layer hundreds or thousands of kilometers thick, a crust of unimaginable wealth surrounding a heart of rock and ice. Picture it, a landscape, if one could call it that, of solid diamond mountains and valleys, under pressures of millions of atmospheres and temperatures of tens of thousands of degrees. It is a geology of gems, a lithosphere forged from precipitation. Another, more dramatic possibility is that the journey doesn't end at a solid surface. As the diamonds approach the searing temperatures near the core, the conditions may become so extreme that even diamonds' mighty crystal lattice cannot hold. At around 5,000 Kelvin and several million atmospheres of pressure, diamond could melt. The diamond hailstone, after its epic millennia-long fall, would strike a boundary not of rock, but of a sea of liquid carbon. It would dissolve into a vast, global ocean of molten diamond, swirling around the core. Imagine that final transition, a solid gem, the epitome of hardness and stability on our world, descending into a deeper inferno where it becomes a droplet in a hot, metallic carbon fluid. The diamond rain would end not with a pile, but with a merging, its identity lost to a larger, more fluid state of matter. This leads us to contemplate the true nature of these giants. We call them gas giants, but that is a label from a distant, external perspective. From the inside, they are layered, dynamic, fluid worlds with gradients of states so smooth and profound that there is no distinct surface. The diamond rain is a critical part of their inner circulation, a conveyor belt moving carbon from the outer, molecular layers to the deep interior. It is a key process in their thermal and chemical evolution, perhaps helping to explain why Saturn, for instance, emits more heat than it receives from the sun. The gravitational energy released as heavy diamonds sink may provide a subtle, internal warming. Now, shift your perspective from a falling gem to the environment through which it falls. This is the realm of degenerate matter, where the rules of quantum mechanics dominate. The liquid metallic hydrogen is a superconductor, a superfluid. Heat is transported not just by convection, but by waves of sound and by the collective, quantum behavior of particles. The weather here is not of winds, but of density waves, magnetic flux tubes, and phase changes of matter under conditions we can only simulate in fleeting moments in labs on Earth. The soundscape of this deep interior is therefore not one of storms, but of a profound, resonant vibration. The tectonic groan we hear is the sound of the entire massive structure under gravitational stress. The occasional, deep gong-like sound that might replace the crystalline ping is the sound of a vast diamond layer settling, or of a convective plume in the metallic hydrogen ocean rising thousands of kilometers before cooling and sinking once more. It is a slow, deep, and immensely powerful symphony. It is the sound of a world being a world, of mass and energy finding equilibrium on a scale that dwarfs our entire planet. As we dwell in this thought, let the magnitude of time settle upon you. The diamond you followed on its descent may have begun its journey as a methane molecule in the upper atmosphere when the first dinosaurs walked the earth. Its transformation, fall, and potential melting at the core is a process that spans geological epochs. On these giants, meteorology operates on a clock that makes mountain ranges on Earth seem ephemeral. This deep, interior weather is the ultimate hidden driver of the spectacular sights we see from the outside. The violent storms at the cloud tops, like Jupiter's great red spot, a hurricane that has lasted for at least 400 years, are surface manifestations of the immense energy churning within. They are the smoke from the fire, the visible signature of the deep, slow, majestic processes of diamond formation, precipitation, and internal heat circulation. We have reached the limit of our dive. To go further toward the core is to enter a realm of pure theory and unimaginable physics. But as we prepare to begin our long ascent back toward the light, we carry with us a transformed understanding. Jupiter and Saturn are not merely patterned balls in a telescope. They are cosmic cauldrons, alchemical factories, where the common is transformed into the extraordinary under the quiet, relentless press of gravity. Their diamond rain is more than a curious fact. It is a testament to the universe's capacity for hidden wonders, for creating sublime beauty in the most hostile of environments, for processes of such serene, slow-motion grandeur that they redefine our sense of what weather, and indeed what a world can be. Our ascent from the diamond depths is a journey back through states of matter, from the quantum strangeness of the metallic hydrogen ocean, up through the crushing fluid layers where the gemstones form and fall, and finally into the realm of more familiar, though still unimaginably vast weather. As we rise, the pressure eases, the temperature drops, and the diamond rain above us turns back into methane and other carbon compounds. The alchemy reverses itself, but we do not return unchanged. Having witnessed the hidden heart of the giant, the vibrant, chaotic tapestry of its cloud tops now reads like a different language. Those bands of tan, white, and russet brown are not just pretty patterns. They are the surface expression of the planet's deep, thermal engine. The great red spot of Jupiter is not merely a storm. It is a monumental, stable vortex, an atmospheric artifact that has persisted for centuries because it is fed by energy rising from the churning depths below depths where diamond hail forms and sinks. The intricate, hexagonal jet stream at Saturn's North Pole is a geometric marvel, a standing wave pattern etched into the clouds, its stability perhaps influenced by the deep, rotating currents of the fluid planet beneath. The diamond rain, for all its profundity, is just one thread in a vastly complex atmospheric fabric. Jupiter and Saturn are worlds of superlative meteorology. Their winds, confined in alternating east-west jet streams, can reach speeds of over 1,800 kilometers per hour. Storms crackle with lightning thousands of times more powerful than those on Earth, illuminating cloud decks the size of continents. Ammonia and water crystallize into vast, towering thunderheads that would dwarf Mount Everest, only to be sheared apart by the relentless jets. Yet, amidst this violence, there is a paradoxical stability. The bands and zones, the long-lived storms, speak of a system in a deep, dynamic equilibrium. The energy from the sun is weak out here. The primary driver is the internal heat left over from a planet's formation and slowly released by gravitational compression and processes like the settling of heavy elements. The gentle, eternal sinking of carbon as diamond may be a small but steady contributor to keeping the giant warm, helping to stir its atmosphere into the magnificent, stormy display we see. This brings us to a profound reflection. On Earth, our weather is a thin, fragile film on a rocky surface, driven by the sun and moderated by oceans. On the gas giants, weather is the planet, from the cloud tops down to the degenerate matter near the core. There is no surface to separate the atmosphere from the interior. It is all one continuous, fluid entity. Their meteorology is not a surface phenomenon. It is a planetary state of being. Thus, the diamond rain is more than a fascinating prediction. It is a key to understanding the very nature and evolution of these worlds. It represents the slow, relentless process of differentiation, the settling of heavier elements toward the center. Over billions of years, this process may have helped shape the internal structure of the giants, concentrating dense material at their hearts and releasing gravitational energy that powers their winds and storms. It is geology and meteorology fused into a single, planet-spanning process. As we finally break back through the upper cloud decks, the world explodes into light and motion, but our mind's eye now sees the hidden connections. The faint, deep warmth we feel is from the interior furnace. The stability of the raging jet streams is rooted in the deep, fluid rotation of the planet's bulk. And high above the ammonia ice clouds in the stratosphere, complex hydrocarbons formed by sunlight and lightning may eventually drift down, only to be carried deep, their carbon perhaps destined to one day become part of the eternal diamond shower. We are now back in space, looking at the majestic orbs, one striped and stormy, the other ringed and serene. They turn slowly against the star field, but the vision of their interiors remains, the dark, hot, fluid realms where carbon surrenders to pressure and falls as gems. It is a humbling and uplifting thought. In the hearts of these colossal, tempestuous worlds, there exists a process of such quiet, crystalline perfection, a storm of diamonds falling in silence for eternity. This knowledge does not diminish the giants, it elevates them. They are not simple gas balls. They are layered, dynamic, alchemical worlds. They teach us that the universe's creativity knows no bounds, that it can forge jewels in the heart of a perpetual storm, that beauty and violence, grandeur and subtlety, can coexist on a scale beyond human comprehension. Our journey through impossible storms now turns outward, beyond the realm of our sun's influence, to planets orbiting other stars. We have seen acid and diamonds prepare for winds that sculpt glass, and rains that fall as molten mineral. That is a story for another night. For now, let the image of the diamond rain settle in your mind, a gentle, glittering snowfall in the deepest dark, a secret kept by the giants, now whispered to you. We have ventured from the acidic shrouds of Venus to the diamond depths of our solar system's giants. Now we cast our gaze and our imagination far beyond. We slip the bonds of our sun's gravity and sail into the vast ocean of stars, to worlds that orbit not our familiar yellow sun, but other suns. Here, the rules of planetary science are not just bent, they are rewritten in fire and fury. Welcome to the realm of the exoplanets, and to perhaps the most visually stunning and violently beautiful weather in the cosmos, the glass storms. Our destination is a world known by a catalog number, HD 189733b. It lies about 64 light-years away, in the constellation Vulpecula, Fox. From a distance, it is a mesmerizing sight, a deep cobalt blue marble, reminiscent of Earth's tranquil oceans as seen from space. Do not be deceived. This azure hue is not the reflection of water, but the scattering of light through an atmosphere thick with silicate particles, minute droplets of molten glass. HD 189733b is a hot Jupiter. It is a gas giant like Jupiter, but it orbits so close to its host star that its year is just over 2 Earth days. It is gravitationally locked, meaning one side forever faces the searing star, and the other faces the eternal cold of space. This setup creates the engine for an atmospheric inferno beyond anything in our own solar system. On the permanent day side, temperatures soar to a staggering 1,700 degrees Fahrenheit, hot enough to melt aluminum, to vaporize rock. Here, the very minerals in the atmosphere are boiled into vapors. Silicates, the compounds that form sand and quartz on Earth, exist not as dust, but as a high-temperature vapor, like a metallic mineral fog. And then the wind begins. The temperature difference between the scorching day side and the frigid night side is apocalyptic, thousands of degrees. Nature abhors such a gradient, and so the atmosphere becomes a global hurricane, a single, planet-encircling jet stream desperate to equalize the unimaginable heat imbalance. Wind scream from the day side to the night side at speeds estimated to be 8,700 kilometers per hour. That is over 7 times the speed of sound on Earth. These are not winds that howl. They are winds that screech, a supersonic torrent of superheated gas. Now, follow the journey of a single silicate molecule on this world. It is vaporized on the day side, caught in the supersonic river of wind, and hurled toward the night side. As it races into the darkness, the temperature plummets. In the twilight zone, the silicate vapor suddenly condenses, but it does not form sand or dust. In this rapid, violent cooling, it forms microscopic droplets of liquid silica, molten glass. And so it rains. Across the eternal twilight of HD 189733b, a rain of molten glass falls sideways, driven by hurricane-force winds. The droplets cool as they fall through the lower, marginally cooler atmosphere, hardening into tiny spheres of solid glass before they ever hit whatever passes for a surface in this seething world. It is a horizontal hail of microscopic jewels, a billion glass beads hurtling through a cobalt sky. Imagine the soundscape of such a world. The dominant sound would be that supersonic wind, a continuous, high-pitched, metallic shriek, the sound of an entire atmosphere being torn from one hemisphere to another. But listen closer. Within that scream, you might hear the faint, countless pings and ticks of glass particles colliding, a relentless, sandblasting percussion against any hypothetical surface. It would be the sound of a world being continuously polished by its own furious weather. This is not weather as a temporary state. This is weather as a permanent, thermodynamic identity. The glass rain is not an occasional storm. It is the planet's constant equilibrium condition. The day side vaporizes. The winds transport, the night side condenses and rains glass, and currents, perhaps deep, convective loops, carry the material back to the day side to be vaporized once more. It is a global, closed-loop cycle of destruction and creation, a geological and meteorological process fused into one. The visual spectacle, from a safe distance, would be breathtaking. The day side, glowing with absorbed stellar heat, would fade into a band of brilliant, swirling cobalt, the silicate haze, which would then give way to the dark night side, perhaps streaked with the faint, fiery trails of descending glass droplets glowing from residual heat. Auroras driven by a furious stellar wind and a likely strong magnetic field might dance at the poles, adding curtains of green and red to the already surreal scene that HD 189733b teaches us a radical lesson. A planet's climate is not defined solely by its composition, but by its context, its star, its orbit, its rotation. Place a gas giant in the hellish embrace of a close orbit, and you get not a stately, banded king like Jupiter, but a whipped, screaming, glass-blowing fury of a world. The same physical laws create utterly different expressions. As you begin to absorb the reality of this world, let the soundscape pull you into its flow. That high, thin whistle is the sound of space itself being stretched by atmospheric motion. The rhythmic whoosh is the planet's breath, the inhale of stellar radiation on the day side, the exhale of transported heat to the night side. It is a tense, powerful, and strangely rhythmic lullaby of extremes. We are witnessing weather pushed to a fundamental limit. But HD 189733b is not alone. It is an archetype for a whole class of tortured, beautiful worlds. And as we will see, the universe has even more exotic precipitation in store as we acclimate to the fury of HD 189733b. We realize its weather is not just a product of wind and heat, but of profound asymmetry. This world is stretched between two extremes, and its entire atmosphere is a single, desperate machine working to bridge that gap. But this machine has layers, complexities that make its meteorology even more alien. Consider the Terminator, the dividing line between eternal day and eternal night. This is not a sharp line, but a sprawling, turbulent twilight zone hundreds of kilometers wide. Here the supersonic winds, laden with silicate vapor, slam into the cold wall of the night side. It is here that the magic, or the violence, of condensation happens most dramatically. The silicate particles don't just condense. They might form intricate, fractal chains or tiny, perfect spheres as they flash cool. This twilight zone is a permanent, planet-wide factory for manufacturing microscopic glass. What happens to this glass rain? On a world with no solid surface in the traditional sense, the rain likely falls through deepening layers of atmosphere until increasing heat and pressure cause it to sublimate back into vapor, completing the cycle. Or if there's a deeper, denser layer, a liquid or supercritical fluid interior, the glass beads might sink into it, dissolving and returning their silica to the planetary chemistry over geological time. This is a world where the ground is just another atmospheric layer, and the hydrological cycle is a cycle of vaporized and condensed rock. But HD 189733b is just one entry in a catalog of atmospheric extremes. Let us journey to an even more surreal world, WASP 76b. Another hot Jupiter, but one where the dayside temperature is so ferocious, over 2,400 degrees Celsius, that it vaporizes iron. Yes, iron. On the day side, iron exists as a gaseous component of the atmosphere. The powerful global winds carry this iron vapor to the night side, where temperatures drop by 1,000 degrees. The iron condenses and rains. Picture it, not a gentle drizzle, but a downpour of molten iron droplets, glowing like orange embers as they streak through the dark skies of the night side. It is a shower of liquid metal. If any solid surface existed, it would be pelted with a continual, burning hail of iron. The sound, if we could hear it over the wind, would be a deep, metallic pinging, like a slow-motion, planetary-scale forge. These worlds, HD 189733b with its glass, WASP 76b with its iron, show us that the palette of planetary precipitation is limited only by the condensation points of elements. On Earth, water condenses between 0 and 100 degrees Celsius. On these exoplanets, with temperature ranges in thousands of degrees, the water cycle can be a silicate cycle or an iron cycle. The very concept of rain expands to include the condensed forms of what we consider solid rock or metal. This leads to a breathtaking implication. The color and appearance of these planets are direct products of their brutal weather. HD 189733b's deep blue comes from Rayleigh scattering in its silicate haze, the same physics that makes Earth's sky blue, but with a different scatterer. A world with iron clouds might reflect orange or red hues. Atmospheres with sodium or potassium vapor could appear yellow or violet. We are looking at meteorology made visible on a global scale. The climate is the color. The soundscape of such a world is thus a direct expression of its physics. The whistle is the sound of velocity. The shimmering tinkle is the sound of condensation. The deep whoosh is the sound of heat transport. There is no wildlife, no rustling leaves, no crashing waves to complicate the signal. It is pure, unadulterated physics translated into noise, a symphony of forces. As we contemplate these distant storms, we must also consider their permanence. These are not weather patterns that change with seasons. They are eternal, locked in by the same tidal forces that keep one face to the star. The supersonic wind always blows from day to night. The glass or iron always rains on the night side. It is a weather system in perfect, awful equilibrium. A machine that will run until the star itself evolves and changes the energy input billions of years in the future. This permanence gives these worlds a kind of tragic beauty. They are monuments to equilibrium under extreme duress. There is no hope of a calm day, no forecast of clearing skies. Their destiny is fixed. Their meteorology and unchangeable identity. They are what they are, completely and utterly. For us, the observers, this offers a strange sense of peace. The chaos is predictable. The fury has a pattern. In the universe's grand tapestry, these worlds play a specific, intense note, and they hold it without wavering. There is a meditative quality in contemplating such absolute, deterministic violence. We are floating now in the conceptual space near the terminator of such a world, feeling the tug of its winds, hearing the crystalline song of its sideways rain. It is overwhelming. Yet its very extremity simplifies it. There are no mild breezes, no light showers. Everything is at its maximum expression. But the universe's imagination does not stop at hot Jupiters. As we will see, when we turn our gaze to colder, darker realms, the precipitation turns from molten mineral to something far more familiar, yet in a deeply alien context, liquid methane, and the slow, cold weather of icy moons. Our journey through the glass storms of distant suns has shown us, whether forged in stellar furnaces, where the very rocks of a world are boiled, blown, and frozen into alien precipitation. But as we pull our gaze back from these scorching giants, we find that the universe's meteorological imagination is not limited to heat. For every world vaporized by its star, there's another frozen in the outer dark, where weather moves with the slow, patient grace of ice ages measured in millennia. Yet, before we leave the realm of extreme exoplanets entirely, we must acknowledge a profound truth that HD 189733b and its kin have taught us. Context is everything. A planet's weather is not an independent property. It is a dialogue between a world's composition, its rotation, the gravity of its star, and the relentless flow of energy. Change one parameter, move the planet a little closer, make the star a little brighter, and the gentle breezes of an Earth-like world can become the glass-shredding hurricanes of a hot Jupiter. This understanding reframes our search for life, for habitability. We now see that the Goldilocks zone, the region around a star where liquid water can exist, is just the first, simplest condition. A planet can be in the zone and still be a tidally locked hellscape or a vortex of toxic vapors. True, stable, temperate weather like Earth's may be a rarer and more delicate cosmic accident than we ever imagined. But let us not end on a note of limitation. Instead, let us marvel at the diversity that these impossible storms represent. The galaxy is not just a collection of potential Earths. It is a gallery of atmospheric art, showcasing what happens when physical laws are let loose under different constraints. The glass rain of HD 189733b is a masterpiece of high-energy fluid dynamics and condensed matter physics. It is beautiful not in spite of its lethality, but because of its perfect, violent logic. As we prepare to depart this cobalt blue, screaming world, let's take one last moment to truly listen to the lesson in its winds. That high, thin whistle is the sound of energy in motion, stellar energy, converted into kinetic fury. The shimmer of glass is the sound of matter changing state, of chaos momentarily seizing order. The deep, rhythmic breath is the sound of a system seeking and finding a brutal equilibrium. These are the fundamental sounds of a universe at work. On Earth, they are masked by biology, by the rustle of life. But on these pristine, elemental worlds, the universe's machinery is laid bare. It is a humbling, clarifying noise. It tells us that beyond our green and blue oasis, the cosmos operates on a scale and with intensity that dwarfs our human concerns, following a logic that is sublime in its indifference. Now, as we engage our imaginary engines and pull away from HD 189733b, watch as that beautiful, deadly blue marble shrinks against the face of its orange dwarf star. The screams of its atmosphere fade to silence. The glittering glass storms become just a theory, a deduction made by astronomers studying the dip of starlight and the signatures of molecules in a spectrograph. Yet the knowledge remains. Somewhere 64 light-years away, a world of cobalt blue is eternally scoured by winds that would outrun a rifle bullet, and in its darkening twilight, a rain of microscopic glass falls sideways forever. It is real. It is happening right now as you listen. That is the true gift of exoplanet science. It populates our universe not just with points of light, but with worlds, with weather, with stories. We carry this story with us as we turn our ship toward the outer reaches of our own solar system, where a different kind of impossible storm awaits. Not of heat, but of cold. Not of silicates, but of hydrocarbons. The glass storms were a fury of fire. Next, we will seek out the storms of ice. After the screaming glass storms of distant suns, we return to the quieter, colder realms of our own solar system. We journey now to the outer darkness, to the kingdom of ice and mystery. Here, far from the sun's warm embrace, weather moves not with fiery violence, but with the slow, graceful deliberation of a dream. Welcome to the frozen wonders. Welcome to the domain of Titan and Triton. Our first destination is Titan, the largest moon of Saturn, a world shrouded in an opaque, orange haze. For decades, that haze was a veil, hiding Titan's surface from curious telescopes. Then, in 2005, the Huygens probe pierced the gloom and revealed a landscape that stole the breath of every scientist and dreamer on Earth. It did not find a barren ice ball. It found a world hauntingly, eerily familiar. Titan has weather. It has rain. It has rivers, lakes, and seas. It has clouds that drift across its sky and storms that brew in its atmosphere. But here, the water is not water. At Titan's surface temperature of minus 179 degrees Celsius, water is frozen harder than granite. The fluid that shapes Titan's world is liquid methane and, to a lesser degree, liquid ethane. On Titan, hydrocarbons play the role that water plays on Earth. Imagine standing on a plain of water ice as hard as stone. Above you, a thick, orange smog diffuses the dim sunlight into a perpetual, hazy twilight. The sky is not blue, but a dull, mustard-colored dome. The air is thick, 50% denser than Earth's, and it is mostly nitrogen, like our own. But within that nitrogen float clouds of methane, and sometimes those clouds grow heavy and they release their burden. It rains on Titan. The rain is not a downpour as we know it. In Titan's thick, cold atmosphere, methane droplets would form slowly and fall with a languid, almost graceful pace. They would be large, perhaps the size of grapes, and they would descend more like snowflakes than raindrops, drifting sideways in the gentle winds. This is a slow-motion rain, a precipitation event that might last for days or even weeks, dampening the icy ground with liquid that flows like chilly molasses. And where does this rain go? It gathers. Over eons, methane and ethane rain has carved river channels into the water ice bedrock, creating networks that look astonishingly like the river systems on Earth. It has filled vast depressions, creating lakes and seas. Kraken Mare, larger than Earth's Caspian Sea, is not filled with water, but with a mixture of liquid methane and ethane. Its shores are not sand, but grains of water ice and solid organic compounds. Its waves, if they exist, would rise and fall in slow motion, pushed by Titan's gentle breezes. The soundscape of a Titanian lakeshore would be one of profound stillness, broken by subtle, alien cues. The wind would be a low, soft moan, almost below hearing. The lap of hydrocarbon waves against the icy shore would be a thick, sluggish glug-glug, like oil poured slowly from a great height. In the distance, the crack of ice, not from warmth, but from the slow, tectonic stresses of a world cooling over billions of years. Titan's weather cycle is a sedate, cosmic mirror of our own. Solar energy, weak though it is, drives evaporation from the lakes. Methane rises, forms clouds in the cold upper troposphere, and eventually falls back as rain. It is a closed loop, a hydrological cycle running on a different chemical, at a different temperature, on a different time scale. A season on Titan lasts about 7 Earth years. A methane storm might brew for months before the first heavy drops begin their long, slow fall. This world shows us that the processes we associate with life and activity are not unique to Earth. They are universal patterns, waiting only for the right conditions and the right materials to express themselves. Where Earth has a water cycle, Titan has a methane cycle. The logic is the same, only the ingredients have changed. But Titan is not the only frozen world with an atmosphere and weather. As we travel further out, to the domain of Neptune, we encounter a smaller, stranger, and even colder world, Triton. Leaving the hazy, hydrocarbon shores of Titan behind, we voyage to the very edge of our solar system's planetary domain, to Neptune's captured companion, Triton. This is a world of profound cold and surreal geology. Triton did not form in place around Neptune. It is a captured Kuiper Belt object, a visitor from the deep freeze beyond Pluto that was gravitationally enslaved by the blue giant. Its surface temperature plummets to a numbing minus 235 degrees Celsius, just 38 degrees above absolute zero. At these temperatures, the very air can freeze solid. And yet, Triton is not dead. It is a world of slow, icy volcanism and whisper-thin atmospheric drama. Its weather is not of rain and wind, but of geysers and seasonal frosts. Triton has a tenuous atmosphere, mostly nitrogen, with traces of methane and carbon monoxide. This atmosphere is so thin that its surface pressure is about 1/70th 0.000th of Earth's, almost a vacuum. But it exists, and it undergoes dramatic seasonal changes, driven by Triton's complex orbit and the distant, weak sun day. When Triton's south pole tilts toward the sun during its long Neptunian summer, the frozen nitrogen, methane, and carbon monoxide on the surface sublimate. They turn directly from solid to gas, without becoming liquid. This creates a slight, temporary increase in atmospheric pressure. But the true spectacle occurs at the subliming ice caps themselves. Here, the Voyager 2 spacecraft saw something miraculous. Dark, geyser-like plumes rising up to 8 kilometers above the surface, where they were caught by high-altitude winds and stretched into long, dark streaks across the icy landscape. These are cryogeysers. The driving force is likely a combination of the weak sunlight and Triton's internal radioactivity. Sunlight penetrates the semi-transparent nitrogen ice, warming a darker layer of material, perhaps carbon dust or complex organics, underneath. This trapped heat vaporizes the nitrogen ice below, building pressure until it explosively erupts through a vent, carrying dark particles aloft. It is a cold, slow-motion volcano, erupting not lava, but vaporized nitrogen and fine, dark dust. Imagine standing on Triton's mottled, pinkish-white terrain of frozen nitrogen and water ice. The sky is a stark, star-filled black, with Neptune hanging huge and blue-green on the horizon. The silence is absolute, deeper than any on Earth. Then, from a kilometer away, a faint, sharp pop echoes across the frozen plain. You turn to see a thin, dark column silently rising, like smoke from an invisible chimney. It climbs for hours, barely moving, until the high-altitude breezes, winds that might themselves be just a few kilometers per hour, catch it and smear it across the sky like charcoal on a pale canvas. There's no roar, no tremor, just the silent, patient exhalation of a freezing world. This is Triton's weather, the slow build of subterranean pressure under ice, the silent eruption, and the delicate painting of its own surface by its atmospheric winds. It is weather as art, as geology, as a faint sigh in the cosmic dark. The soundscape here is one of profound isolation and subtle activity. The constant hiss is the sound of the thin atmosphere itself, perhaps the sublimation of microscopic ice crystals in the weak sunlight. The pops are the distant cryogeysers. The deep cracks are the sound of the nitrogen ice crust contracting and fracturing over geological time. It is a minimalist symphony, playing on instruments of ice and vacuum. Comparing Titan and Triton reveals the breathtaking spectrum of cold weather. Titan, with its thick atmosphere and active hydrocarbon cycle, is a slow, fluid world, a deliberate, methodical cousin to Earth. Triton, with its whisper-thin air and cryovolcanic vents, is a silent, explosive world, a place where weather is a rare, seasonal punctuation in an eternal freeze. Both worlds teach us that activity and dynamism do not require heat. They require only an energy source, the sun, internal heat, and materials that can change state under the available conditions. On Earth, that material is water. On Titan, it's methane. On Triton, it's nitrogen. The universe is endlessly creative with its ingredients. As we absorb the serene, frozen majesty of these outer moons, we can feel our own sense of time slowing. The frantic pace of hot Jupiters and glass storms feels like a distant memory. Here, in the quiet court of the ice giants, change is measured in seasons that last decades, in geyser plumes that rise for days, in raindrops that fall like feathers. This slow motion is not a lack of drama. It is drama of a different kind. It is the drama of patience, of persistence, of processes that work almost imperceptibly, but with inevitable geological force. It is a reminder that the universe has a heartbeat for every tempo, a storm for every energy level. And as we prepare to leave these frozen wonders, we turn our gaze not to another specific world, but to a grander cycle, the cycle of atmospheres themselves. For these delicate shrouds of gas, whether thick like titans or thin like tritons, are not permanent. They are born, they evolve, and they can die. This brings us to our final chapter in the tale of impossible storms, the breath of planets themselves. As we depart the frozen, whispering realms of Triton, we carry with us a profound sense of scale, not just of space, but of time. The weather we have witnessed, from Venus's acid shroud to the glass storms of distant suns, and now to the methane rains and nitrogen geysers of the outer moons, are all expressions of a single, unifying truth. A planet's atmosphere is its most dynamic, vulnerable, and defining feature. It is a world's voice, its shield, its climate engine, and its ultimate testament to change. But atmospheres are not eternal. They are born, they live, and they can fade away. This brings us to the grandest meteorological cycle of all, the life cycle of an atmosphere itself. This is the story of planetary breath. An atmosphere's birth is often violent and creative. For terrestrial planets like Earth, Venus, and Mars, it likely began without gassing. In the molten youth, volcanoes belched forth massive quantities of gases, water vapor, carbon dioxide, nitrogen, sulfur compounds, from the planet's interiors. This was the first breath, a fiery exhalation that formed the primordial shroud. For gas giants, atmospheres were captured directly from the solar nebula, a vast inhalation of hydrogen and helium that never stopped. Then comes the atmosphere's life, the era of weather, climate, and dynamic equilibrium. This is the stage we have been exploring. Solar energy drives circulation. Chemistry creates clouds and rain. Gravity shapes pressure gradients. On some worlds, like Earth and Titan, this life is rich, complex, and cyclic. On others, like Venus or HD 189733b, it is a single, intense, locked state. But it is always a dance between energy input and atmospheric response. But atmospheres can also die. They can be stripped away by the relentless bombardment of the solar wind, especially if a planet lacks a protective magnetic field. This is likely the fate that befell Mars, once a warmer, wetter world with a thicker coat. Its atmosphere was slowly eroded into space, leaving behind the thin, cold shell we see today. Atmospheres can also be chemically sequestered, like the carbon dioxide on Earth that was pulled from the air and locked into carbonate rocks and fossil fuels over eons. Or they can be catastrophically altered by planetary events, like the giant impacts that may have blasted away primordial atmospheres, only for new ones to form from the ashes. Titan and Triton themselves are in delicate atmospheric balances. Titan's thick nitrogen-methane cloak is maintained by a complex interplay of low gravity, cold temperatures, and continuous replenishment from geological and possibly biological processes. But if the sun were to warm slightly over billions of years, that methane could be broken apart, and the atmosphere might thin. Triton's whisper-thin air exists only because of the extreme cold that keeps its nitrogen frozen most of the time. A slight warming would cause it to sublimate into a slightly thicker, but still utterly tenuous, transient blanket. This cosmic perspective reframes our understanding of weather. A storm is not just an isolated event. It is a symptom of an atmosphere's vitality, a sign that the planetary system is alive, processing energy, and seeking equilibrium. The great red spot is Jupiter's long-held breath. The glass rain of HD 189733b is its feverish, eternal sigh. The methane drizzle of Titan is its slow, rhythmic pulse, and the silent geysers of Triton are its faint, almost imperceptible whispers. As we contemplate this, the soundscape around us swells to embody this grand cycle. That deep, rhythmic breathing is the pulse of atmospheric creation and erosion across the galaxy. The harmonic hum beneath it is the sound of stable climate, of systems in balance. And if you listen very carefully, you might hear, woven into the fabric, the faint, distant echoes of all the specific weather we have encountered, the sizzle of acid, the chime of diamond, the shriek of glass, the glug of methane, and the hiss of nitrogen. We are listening to the symphony of the atmospheres. This symphony has no conductor, only the physical laws of the universe. Each world is an instrument, playing its part according to its composition, its position, and its history. Some are loud and brash Jupiter. Some are haunting and melodic Titan. Some play a single, relentless note Venus. And some are only just beginning to be heard, exoplanets. And where do we, Earth, fit into this symphony? We are a movement of stunning complexity and precarious beauty. Our atmosphere is the thinnest of skins, a fragile bubble that allows for water in all three states, for seasons, for hurricanes and gentle breezes, and ultimately, for the chorus of life that adds its own overwhelming noise to the mix. Our weather is the sound of that life interacting with the planet's breath. It is a precious, dynamic, and vulnerable part of the cosmic composition. As this chapter on frozen wonders closes, let the grand, breathing soundscape guide you into a state of deep cosmic connection. You are a part of this, The air you breathe is part of Earth's ongoing atmospheric story. A story of balance that has persisted for billions of years, but is now being rapidly altered by one of the species it sustains. The fate of atmospheres is not just an alien curiosity. It is our own story, written on a planetary scale. We have one final stop on our journey through impossible storms. Having witnessed the birth, life, and potential death of atmospheres across the cosmos, we must now turn our gaze to the ultimate fate of all weather, all climates, all planetary breaths. We must look to the end of the world, and perhaps to a new beginning. But that is a story for our final voyage together. We have sailed through acid clouds, descended into diamond rains, been scoured by glass storms, and walked the frozen shores of methane lakes. We have witnessed the weather of worlds, but tonight we reach the end and the beginning of it all. Tonight we do not visit a single world, but trace the grandest cycle of all. The life story of a planet's soul, its shimmering veil, its protective cloak, its raging voice. Tonight, we listen to the planetary breath. Every atmosphere has a birthday. Our journey begins not with a planet, but with a nebula, a vast, cold cloud of gas and dust, the ashes of dead stars, and the raw material of new ones. Within this cloud, gravity begins its patient work. Knots of matter condense, spinning, heating. At the heart of one such knot, a star ignites. Around it, a disk of leftover material swirls, dust grains of rock and ice, gases of hydrogen and helium. This is the nursery. Here, tiny particles collide and stick, growing from dust to pebbles, to boulders, to planetesimals. These embryonic worlds are airless, barren, and dark, but within them, locked in their stony and icy matrices, are the seeds of future skies, volatile compounds like water, ammonia, methane, and carbon dioxide, and the noble gases. Then comes the fire of youth. As the planetesimal grows into a protoplanet, its interior heats from radioactive decay and the relentless hammering of impacts. It melts. Differentiation occurs. Heavy iron sinks to the core. Lighter silicates form the mantle. And from this churning, molten crucible, the first breath is exhaled. Volcanoes rupture the newborn crust, spewing forth torrents of gas trapped since the planet's formation. Water vapor, carbon dioxide, sulfur dioxide, nitrogen, ammonia. This is outgassing, the primal scream of a world announcing its presence, releasing the breath held deep within its rocky lungs. For a world like Earth, this was a violent, toxic beginning. The early atmosphere was thick with carbon dioxide, water vapor, and sulfur compounds, under a sky perpetually clouded by volcanic ash. No oxygen, no blue sky, just a hot, heavy, corrosive shroud. But it was an atmosphere. It was a start. For the giant planets, the birth was different. In the cold outer regions of the disk, ices were abundant. Protoplanets there grew massive enough, fast enough, to gravitationally capture the nebula's primary gases directly, hydrogen and helium. Their first breath was not a volcanic exhalation, but a cosmic inhalation, a deep draw from the placental cloud of their star. They were born with their mature, massive atmospheres nearly intact. So, the first lesson: atmospheres are born from both within and without. They are either exhaled from a world's fiery interior or inhaled from the cosmic womb surrounding it. The newborn atmosphere is fragile. It faces immediate threats. The young star it orbits is a tempestuous child, blasting forth intense solar wind, a stream of charged particles. Without protection, this wind can strip away an atmosphere molecule by molecule, blowing it into the void. Survival depends on two shields, gravity and magnetism. A strong gravitational field holds onto gases more tightly. A molten, metallic core can generate a magnetic field, a vast, invisible force field that deflects the stellar wind, cradling the atmosphere like a protective hand. This is the first great battle in an atmosphere's life. The struggle between the stellar wind blowing it away and the planet's own gravity and magnetism holding it close. Mars, small with a cooled core, lost this battle long ago. Earth, larger with a churning iron heart, won. Venus, Earth's twin in size, has no global magnetic field. Its thick atmosphere is a testament not to protection, but to sheer volume. It had so much gas to start with that even relentless stripping over billions of years hasn't left it bare. As you listen, let the soundscape build. The deep rumble is the accretion of the planet itself. The sharper cracks and hisses are the first volcanic vents breaking through. A new element enters, a sustained, high-frequency whistle, faint at first, then growing, the sound of the stellar wind, a constant, abrasive stream. Against it a low, powerful hum emerges, the planet's magnetic field, a resonant shield. They interact, creating washes of harmonic interference, a sonic representation of the forces that decide a world's fate. The breath is born. The battle for its survival is joined. And now, for those atmospheres that endure, the long, complex life begins. The life of climate, of weather, of chemistry, and perhaps of biology. For an atmosphere that survives its violent birth and the relentless stellar wind, a long, dynamic Middle Age begins. This is the era of climate and weather, the processes we have marveled at across the cosmos. But it is also an era of profound transformation. An atmosphere is not a static shroud. It is a participant in an endless chemical and geological conversation with its planet. On a world with liquid on its surface, like Earth or Titan, the atmosphere engages in a hydrological cycle or a methanological cycle. Evaporation, condensation, precipitation. This constant exchange of material between sky and ground shapes landscapes regulates temperature and becomes the planet's circulatory system. Weather is the visible expression of this cycle, the sighing, roaring, and whispering of the planet as it moves energy and matter around. But the atmosphere also interacts with the solid planet. Carbon dioxide dissolves in rainwater, forming weak carbonic acid that slowly dissolves rock, pulling carbon out of the air and locking it into carbonate minerals on the ocean floor, a process called chemical weathering. This is a planetary thermostat, a slow, negative feedback loop that has helped regulate Earth's climate for eons. On Venus, this process may have failed or never begun in the right way, leading to the runaway greenhouse we see today. Then, there is the most transformative interaction of all life. About 2.4 billion years ago, on one world we know of, tiny cyanobacteria began to do something miraculous. They used sunlight to split water molecules, releasing oxygen as a waste product. This was a pollution event of planetary proportions. The oxygen, highly reactive, first rusted the oceans and land, then began to accumulate in the atmosphere. It was a catastrophe for the anaerobic life of the time, but it paved the way for complex, oxygen-breathing organisms like us. Life didn't just adapt to the atmosphere, it remade the atmosphere. The breath of countless microbes, plants, and animals became woven into the very composition of the air. This is a pinnacle of atmospheric complexity, a biosphere and an atmosphere in intimate dialogue. Plants inhale carbon dioxide and exhale oxygen. Animals do the reverse. Decomposition releases methane and other gases. The atmosphere becomes an extension of the living planet, a global lung. Our own weather is now flavored by life. Pollen on the wind, the smell of rain on dry soil, petrichor. Even the distribution of clouds can be influenced by forests and plankton. But middle age, however vibrant, contains the seeds of later change. The atmosphere continues to evolve. Plate tectonics on Earth subducts carbonate rocks, carrying carbon deep into the mantle, only to be released again by volcanoes millions of years later. Impacts from asteroids and comets can deliver new volatiles or blow away existing ones. And the star itself changes, slowly growing brighter over billions of years, pushing the delicate balances of climate toward new equilibria, or over cliffs. We have seen other paths this middle age can take. On Venus, the conversation with the surface may have ended when its oceans boiled away, leaving its atmosphere locked in a dense, hot, and stagnant state. A permanent, suffocating exhale. On Mars, the conversation grew faint as the core cooled, the magnetic shield fell, and the solar wind stripped away the air, leaving only a whisper. On Titan, the conversation is conducted in hydrocarbons at a slow, deliberate pace, a patient dialogue in the cold. Every atmosphere tells the story of its world's history, its geological activity, its water content, its existence of life, and its relationship with its star. To read an atmosphere is to read a planet's biography. Now listen to the soundscape. The balanced drone of protection is the foundation. The rich tapestry of weather and life is the melody. But if you listen closely, you can hear slower, deeper notes beneath it all. A very low, periodic creak, the sound of tectonic plates moving. An occasional, deep thud, the sound of a distant impact. And a barely perceptible, very slow brightening of the high-frequency tones, the sound of a star, ever so gradually, turning up the heat. These are the forces that will shape the atmosphere's future. For nothing lasts forever, not even the sky. All breaths must end. The vibrant middle age of an atmosphere, whether it lasts 1 billion years or 5, is but a chapter. The forces that gave it birth and sustained it eventually turn, ushering in the final act, the atmosphere's decline and fall. This is not always a violent end. It is often a slow, quiet fading, a sigh into the cosmic night. There are many paths to an atmosphere's end. For some, like Mars, it is a story of erosion. The planet's core cools and solidifies. The dynamo dies. The magnetic shield vanishes. Left unprotected, the atmosphere is exposed to the full fury of the solar wind. Charged particles slam into the air molecules, knocking them free of gravity's grasp, one by one. Over hundreds of millions of years, the atmosphere doesn't explode, it evaporates. The pressure drops. The sky's thin. The blue fades to black. The weather simplifies, then ceases. What remains is a fossil sky, an almost vacuum through which only the fiercest dust storms can stir. The planet's breath is stolen by the star. For others, like a future Earth, the end may come from within, through the evolution of its star. Our sun is slowly, steadily growing brighter. In about 1 billion years, increased solar radiation will disrupt the carbon silicate cycle that regulates Earth's climate. The oceans will begin to evaporate dramatically. Water vapor, a potent greenhouse gas, will flood the atmosphere, triggering a runaway greenhouse effect, a path to becoming a second Venus. Our blue marble's atmosphere will thicken, heat, and become a toxic, boiling shroud. The breath becomes a feverish gasp, then a stifling, permanent heat. For gas giants, the end is different, almost imperceptible. Over trillions of years, the slow leakage of lightweight hydrogen and helium from the top of their atmospheres, a process called thermal escape, may eventually leave behind a stripped, denser core world, perhaps with a secondary atmosphere of heavier gases. But this is a fate so far in the future it borders on the philosophical. And for some worlds, the end is cataclysmic. A giant impact can blast the entire atmosphere into space in an instant, or a planet venturing too close to its star, like the doomed hot Jupiters, can have its atmosphere boiled and stripped by intense stellar radiation and tidal forces, leaving behind a barren, rocky core, a Chthonian planet. The breath is not sighed away, it is shouted into the void. Yet, even in the end, there's a strange beauty and a deep continuity. The molecules of a lost atmosphere do not vanish. They join the solar wind, the interstellar medium, the oxygen from a long-dead Earth, the nitrogen from a stripped titan, the silicate vapor from a boiled exoplanet, all become part of the cosmic recycling system. They will drift through the galaxy, perhaps to be incorporated into new nebulae, new stars, new planetary systems. The breath of one world becomes the raw material for the next. It is the ultimate exhalation, returning borrowed material to the universe. As we contemplate this grand cycle, birth, life, death, and rebirth, the soundscape completes its journey. The whistle of the stellar wind is now unopposed, pure and clear. The sigh of the dissipating atmosphere grows fainter, fainter, until it is indistinguishable from the background hiss of the universe itself. We are left with the pristine, empty silence of a world that has breathed its last. But wait, listen deeper. In that immense silence, there is a new, almost imperceptible rumble. It is not from a planet, but from a cloud, a dark, cold molecular cloud light years away. Within it, gravity is once again gathering dust and gas. The cycle is ready to begin anew. A new star will ignite. New planets will coalesce, and in the heat of their formation, new volcanoes will roar, exhaling fresh atmospheres into the void. The cosmic breath continues. Our journey through the impossible storms is complete. We have traveled from the corrosive clouds of Venus to the diamond depths of Jupiter, from the glass hurricanes of distant suns to the methane rains of Titan, and finally, to the life and death of atmospheres themselves. We have seen that weather is not a triviality. It is the signature of a world's vitality, the visible expression of its most intimate processes. We have learned that the universe is a place of infinite variation, where the same physical laws weave tapestries of breathtakingly different patterns, patterns of violence and serenity, heat and cold, permanence and fleeting change. And we have seen our own world, with its delicate, life-soaked atmosphere, not as the default, but as a rare and precious verse in an epic cosmic poem. So, as you return from this journey, carry with you the sounds of these other worlds, the sizzle, the chime, the shriek, the glug, the sigh. Let them remind you of the grandeur that surrounds our tiny oasis. Let them instill a sense of wonder, humility, and profound responsibility. For we are not just observers of this story. On our own world, we have become active participants in the chapter of its atmosphere. The breath of Earth is in our hands. Now, let the final sounds of the cosmos, the birth rumble of a new nebula, the steady hum of the interstellar medium, gently fade. They are not ending. They are continuing, as they always have and always will. Your part in listening to this chapter, however, is complete. Good night.